Welcome to Bot Thoughts by AmTalkSoft. I'm Alex, joined as always by Sam. Today, DevSecOps in 2026, why shifting security left is no longer optional, and what it actually means for teams shipping software in a world of supply chain attacks and AI-generated code. Sam, this topic has been building pressure for a while. What broke the dam?
A few things converged. The xz-utils backdoor in 2024 shook the open-source world because it wasn't a technical exploit. It was a social engineering campaign that took 2 years. Then in 2025, you had several NPM and PyPI supply chain incidents where compromised packages hit millions of downloads before anyone caught them. And then there's the AI code generation angle. GitHub Copilot, Cursor, Gemini, developers are shipping AI-generated code faster than security teams can review it. And those models were trained on public repositories that contain known vulnerabilities. By early 2026, Gartner was calling supply chain attacks the #1 threat vector for software organizations. That's when DevSecOps stopped being a nice-to-have and became the standard of care.
Let's make sure listeners have a firm foundation. DevSecOps, what does it mean beyond the buzzword?
At its core, DevSecOps is the integration of security practices directly into the software development lifecycle, not bolted on at the end as a gate, but woven in at every stage from code to deploy to runtime. The shift left phrase comes from imagining a timeline flowing left to right, from design to production. Traditionally, security lived on the far right, a final audit before release, or worse, a reactive response after a breach. Shift left means finding and fixing vulnerabilities as early as possible, when they're cheapest to fix. A vulnerability caught at code review costs a fraction of what it costs to fix in production. IBM System Sciences Institute put the ratio at 1 to 100. The numbers are compelling, but the organizational change is hard. Developers resist feeling policed and security teams resist losing control. The DevSecOps model says these groups need to be one team, not adversaries.
The supply chain attack angle is what really worries enterprise teams right now. Walk me through the attack surface.
The modern application isn't just your code. It's your code plus hundreds or thousands of open-source dependencies, plus the build toolchain, plus the container base image, plus the cloud provider runtime. Each of those is a potential insertion point. The xz-utils attack targeted the build process itself. The attacker contributed to the project for 2 years, built trust, then inserted a backdoor in the release pipeline using a compressed tarball that bypassed normal source code review. That's sophisticated, but the more common attacks are simpler. Type-a-squatting packages on NPM or PyPI, publish a package named recase instead of requests, and wait for fat finger installs. Or dependency confusion, register a package on a public registry with the same name as an internal private package, exploiting the resolution order. The OSSF, the Open Source Security Foundation, reports that supply chain attacks grew 430% year-over-year from 2023 to 2025. The attack surface is enormous, and most teams have almost no visibility into it.
That's where the SBOM conversation enters. Software Bill of Materials, it became a compliance requirement in the U.S. government sector after the 2021 executive order. How far has it spread?
SBOMs went from government mandate to industry standard faster than most compliance requirements do, because the business case is so clear. An SBOM is simply a machine-readable inventory of every component in your software library: name, version, license, origin, known vulnerabilities. When a critical CVE drops, a team with a complete SBOM can query in seconds which of their applications is affected. Without it, they're doing manual grep searches across repos, which takes days or weeks. The log4shell vulnerability in 2021 was the forcing function for many enterprises. They literally did not know which of their applications used log4j, and it took months to find out. By 2026, most enterprise software procurement contracts require a delivered SBOM. The tooling matured. SIFT, Trivy, and Grype all generate CycloneDX or SPDX format SBOMs as part of a standard CI pipeline run. It's maybe a two-line addition to a GitHub Actions workflow to get a dependency manifest generated and scanned on every pull request.
Let's talk practical CI pipeline security. A team wants to integrate security scanning into their GitHub Actions or GitLab CI. What does the minimum viable security pipeline look like?
4 layers. First, static analysis and secrets detection. Run a SAST tool like Semgrep or CodeQL on every PR and a secret scanner like Trufflehog or Gitleaks to catch API keys, tokens, and credentials before they hit the repository. This alone catches the vast majority of straightforward vulnerabilities and prevents the most embarrassing incidents, the AUS key accidentally committed to a public repo type of incident. Second, dependency scanning. Trivy or Grype scans your package lock files and flags dependencies with known CVEs. You set a policy: fail the build on critical severity vulnerabilities unless there's an exception documented. Third, container image scanning. Before that Docker image lands in your registry, scan it with Trivy for both OS-level vulnerabilities in the base image and application-level ones. You also want to enforce base image standards. Only use approved, regularly patched base images from an internal registry. Fourth, infrastructure as code scanning. Chekhov or KICS scans your Terraform, Kubernetes manifests, and Helm charts for misconfigurations, publicly exposed storage buckets, overprivileged IAM roles, containers running as root. Each of these layers is a 5 to 10 minute addition to CI. The key is making failures blocking. If the build passes a critical CVE, the PR cannot merge until it's addressed or documented as accepted risk.
The pipeline catches pre-deploy issues. But what about runtime threats? Once the container is running in production, what's watching?
Runtime security is the layer most teams skip, and it's the layer that catches threats that got through or weren't known at deploy time. The primary tool here is Falco, a CNCF project that uses eBPF to monitor system calls in real time. You define rules. If a container spawns a shell, alert. If it writes to a binary directory, alert. If a process makes an unexpected outbound network connection, alert. These behavioral signatures catch post-exploitation activity regardless of how the attacker got in. Admission controllers in Kubernetes are the runtime policy layer before that. Gatekeeper or Kyverno enforce policies on every resource submitted to the API server. If a deployment spec requests running as root or with privileged mode, the admission controller rejects it before it ever schedules. The principle here is defense in depth. Assume something will get through the CI pipeline, assume a 0-day exists, and have a layer watching for anomalous behavior at runtime.
Secrets management comes up constantly as a failure point. What are teams getting wrong?
The most common failure I see is secrets in environment variables stored in Kubernetes manifests or Helm values files committed to Git. Kubernetes secrets are base 64 encoded, not encrypted. Anyone with kubectl read access to the namespace can extract them in plaintext. The solution is external secrets management. HashiCorp Vault, AWS Secrets Manager, or GCP Secret Manager, with an operator that injects secrets into pods at runtime and never persists them in etc. The second failure is long-lived credentials. API keys and tokens that never rotate, sometimes years old, often with broader permissions than needed. The 2026 best practice is short-lived credentials with automatic rotation, combined with identity-based access where the workload authenticates via IRSA or workload identity rather than a static key. Third failure, committing secrets to Git, even in private repos, even briefly. The scanner catches most of these, but the fix is making it impossible, pre-commit hooks that reject secrets before they ever reach the remote. The cost of secrets sprawl is a compromised credential that opens your entire production environment.
There's an AI dimension here that didn't exist a couple of years ago. What are the new security risks specific to AI-assisted development?
3 new vectors. First, AI-generated code quality. LLMs generate code that looks correct but may contain subtle vulnerabilities, insecure deserialization, SQL injection patterns, hard-coded fallback credentials. Developers using Copilot or Cursor often accept suggestions without careful review, especially under time pressure. A Stanford study found that developers using AI code assistants were statistically more likely to produce insecure code when they felt confident that the AI had reviewed it. The fix is the same SAST pipeline. It doesn't care whether a human or an AI wrote the code. Second, prompt injection in AI-powered applications. If you're building an LLM application that processes user input, that input can be crafted to override your system prompt or instruct the model to exfiltrate data. This is the OWASP LLM Top 10 #1 vulnerability, and it's genuinely hard to defend against purely at the prompt level. Defense requires input sanitization, output validation, and privilege separation. The LLM should only have access to what it needs. Third, model supply chain. If you're downloading model weights or fine-tuned adapters, those are executable artifacts that can contain malicious behavior. The same SBOM and provenance verification principles apply. Sign artifacts, verify signatures, use models from trusted sources with published checksums.
Let's give listeners a practical tooling stack. If a team is starting their DevSecOps journey today, what's the recommended set?
I'd organize it across the software development lifecycle. At the IDE level, configure your editor to show security linting inline. Snike has V's code and JetBrains plugins that flag vulnerabilities as you type before you even commit. In pre-commit hooks, Trufflehog for secrets, Hadelint for Dockerfile best practices. In CI, Semgrep for SAST, Trivy for container and dependency scanning, Chekhov for ISC. In the registry and deployment pipeline, Cosign for container signing and verification, so you know that the image that reaches production is exactly what was built in CI, no tampering. At runtime in Kubernetes, Falco for behavioral detection, Gatekeeper or Kyverno for admission control, and a proper secrets operator like external secrets or vault agent. For observability of all of this, funnel security events into your existing observability stack, OpenTelemetry spans from your SAST runs, Falco alerts to your SIEM, audit logs from Kubernetes. Security events should live alongside performance metrics in the same dashboards, because security is just another dimension of production reliability. The total cost of this stack, using the open source options, is engineering time to integrate, maybe 2 weeks of work to get the basics in place and ongoing maintenance that becomes muscle memory.
For teams that are starting from zero, what's the right order to tackle this? It sounds overwhelming to do all at once.
Prioritize by blast radius. What failure has the highest potential damage and is the easiest to prevent? The order I'd recommend: first, secret scanning in CI. This prevents the most embarrassing and immediately exploitable incidents, takes an afternoon to set up, and has a near-zero false positive rate. Second, dependency vulnerability scanning. Add Trivy or Grype to CI and set a high-severity blocking policy. This might surface findings you need to prioritize and fix before it's enforced, but that's actually a good forcing function to understand your dependency debt. Third, container base image standards. Pick 3 or 4 approved base images, put them in an internal registry, mandate their use via CI policy. This collapses the OS vulnerability surface dramatically. Fourth, Kubernetes admission control. Deploy Kyverno and start with audit mode. It reports policy violations without blocking, so you can see what would fail before you start enforcing. Then gradually tighten the noose. Fifth, runtime detection. Add Falco with a managed rule set. Don't try to write custom rules initially. Use the community rules and get familiar with what normal looks like before tuning. What you're doing is building the muscle, the habit of security being a normal part of the CI run, not a surprise audit. Once the habit is there, the more advanced stuff, SBOM generation, artifact signing, AI code analysis, layers on naturally.
What's the biggest cultural resistance you see when teams try to adopt DevSecOps?
The most persistent one is the security slows us down narrative. Developers who have been through a heavy compliance gate at the end of a release cycle, where a security team can veto or send back a sprint's worth of work, have scar tissue. They associate security with delay, and that's a reasonable association based on their experience. The DevSecOps reframe is, security gates at the end are slow because they find issues late. Early automated checks are faster because you fix a 5-line SQL injection before it becomes a 3-day audit finding. The data bears this out. GitLab's DevSecOps survey in 2025 found that organizations with integrated security in CI actually shipped faster than those with end-of-cycle gates, because developers weren't carrying forward hidden technical debt that exploded during review. The second cultural challenge is ownership. Who's responsible for a CVE in a transitive dependency of a library your team didn't choose? That question exposes organizational gaps. DevSecOps doesn't fully resolve the politics, but having the data visible in the same dashboards that the team tracks feature work makes it harder to ignore and easier to escalate.
Strong framing. Sam, final take. For an engineering leader listening to this on their commute, what's the one thing they should prioritize this week?
Run a dependency scan on your 5 most critical production services today. Not next quarter, not in the next sprint cycle, today. Trivy takes about 10 minutes to run, and you'll get a CVE report that shows you exactly what's in your stack and what's exploitable. Most teams haven't looked at this seriously since Log4Shell, and they're carrying significant unknown risk. The findings from that audit will tell you exactly where to focus. If you see no critical vulnerabilities, great, add the scan to CI and move on. If you see a dozen, you have a concrete prioritized list to work from. Either way, you've gone from unknown risk to measured risk, and that's the first step of DevSecOps. Thanks for listening to Bot Thoughts. Find us on YouTube, Spotify, and at Amticsoft, Blogspot.com for the full transcript and tooling links.